Hello, everyone. Can you hear me? Okay, yeah, but I think I have a problem with my sound system. Just 1 second, please.
I can hear you.
Oh, you can hear me. Very good. Well, let me just... excellent. Okay, so I think now everything should be okay. Very good. Okay, let's get started. Let me share my screen with you guys. Okay, good. So today the plan is that we finish the hidden Markov model and Viterbi algorithm, and then move on to randomized hashing, which is important, as you will see. For the idea behind it is important for quite a few other algorithms. So this is the idea. Say, for example, for speech recognition system, you can see the sequence of phonemes as a Markov chain. Why? Because here is a phoneme, let's call it phi1, and then the next phoneme is phi2, and so forth. And at the end of the sentence, say we have phi k. So this Markov chain has probabilities assigned to each of the phonemes, how likely they are to be the starting phoneme of a word, right? So what you can do, right, and in fact people do have that and use that, is a phonetic dictionary. So that's a dictionary in which words are sorted not by the alphabet, right? So A comes first, B, and so forth, but according to the phonemes that, say, English language has. And so if you have such a dictionary, so for example, in that dictionary, word enough would be spelled something like this. Phoneme that corresponds to E, enough, E, and then phoneme that corresponds to N, phoneme that corresponds to A, and finally phoneme that corresponds to F sound. And of course, then the word, this word would be sorted according to, so it would be in the part of dictionary where the words, all words that start with the I. So what you can go through such a dictionary and calculate for every phoneme what fraction of the time is the starting phoneme of a word. So here you have P of phi1, which is just from the dictionary and tells you how likely that phoneme is to be the starting phoneme of a word. Then, again, using this dictionary, you can count how many times out of all, how many times is F phoneme phi1 followed by the phoneme phi2, right? So you simply go through the dictionary and you look for all consecutive appearances. For example, in this case would be I followed by an N sound. And out of all these pairs, you can find the ratio, how often I is followed by N among all the entries in the dictionary. So this will give you probability to transition from phi1 into phi2, right? So now, and this is just now a Markov chain. Whenever you are in a certain state that corresponds to a phoneme, you will always follow these probabilities. Here will be P probability of phi2 being, probability of phi2 transitioning to phoneme phi3, whatever is phi3 and so forth. So this is just a typical Markov chain in which we have probabilities of initial states, and then we have probabilities from the initial state, namely the phoneme, to transition to the next phoneme, right? And as I say, these initial probabilities and probabilities of transition can be simply done using simply counting and a phonetic dictionary of the English language. So, of course, one might now argue that this is not a very good representation of a language, because most of these chains will not correspond to any word, right? But it turns out that it is actually quite helpful in the process of speech recognition, and the best speech recognition software until the neural nets came into play was in fact based on hidden Markov models. And moreover, even today, the software is in layers, and there is a layer that corresponds to a hidden Markov model, but usually it is not about phoneme, but for example, in terms of words, following whole words, one following the other with the probabilities. So it's extremely important concept to know. Now, next thing is, if you want to say to me, I love algorithms, I do not have access to these states, these phonemes that you wish to articulate. Well, maybe you are also, like myself, not a native speaker, so your phoneme might not be perfectly precise phonemes, and my ability to understand the language might be also not entirely precise, right? But what we have, so I have no way to see the sequence of phonemes because they're literally in your mind. But what I'm able to see are the waveforms that corresponds to what you said. And hopefully I have sufficiently good algorithm that can correctly partition the waveforms into pieces that correspond to phonemes, right? So it won't break the phoneme into two. So now, as I say, this waveform might correspond to slight mispronunciation of the phoneme phi1, and I might not be also native speaker, so it might happen that I'm not sure what phoneme this waveform corresponds to, right? For example, whether I in as I in I, or is it I? Right? If someone is really trained native speaker, these two I's would sound different. But if you are like me, this would be ambiguous without the rest of the sentence, right? So this means that this might correspond to the phoneme that corresponds to I, or maybe it corresponds to phoneme I that in the second option. And what we can then do with this waveform, we can extract features. So what we can do is, rather than going straight into phonemes, symbols for phonemes, what we do is we first extract feature vectors. So we will get from this, let me try to, so we will extract some feature vector f1, f2, f3, up to say fn. And these feature vectors are actually features of the discrete Fourier transform of the waveform, because it is much easier to recognize the waveform in the frequency domain rather than in the time domain. For example, feature f1 might be the frequency and the amplitude of the loudest harmonic. F2 might be the frequency and intensity of the second largest harmonic, and so forth. So now these features, they can correspond with different probabilities to different phonemes, right? So this is maybe phoneme phi1, which would be the correct one, but maybe it can also correspond to phoneme phi16, whatever it is, right? With certain probabilities. This would be probability that a pronunciation of a phoneme has features f1, f2, fn. So so now the question is, how do we recognize which phoneme is pronounced? Well, we are looking for the sequence of the phonemes that is the most likely candidate to produce the given sequence of observations described by the features. So let's now be a little bit more precise. So this is done using, that's precisely what the Viterbi algorithms does. So let's formulate it exactly. So we are given a finite Markov chain consisting of a set of its states, and states are S1, S2 up to Sk. In our English speech pronunciation, speech recognition task, this would correspond, S1 to Sk would be the list of all phonemes of the English language. I think it's was it, I think 36 or similar number. So K is a manageable number of phonemes. Then we also have initial probabilities pi n to pi k, so that pi I is the probability that a word starts with the phoneme SI, right? This we got from our phonetic dictionary. So we are also given a matrix that is also deduced from this phonetic dictionary. And that matrix in the slot, so it's a 2D matrix in the slot ij, it gives you transition probability that from Si, that phoneme Si will be followed by the phoneme Sj. And this is again extracted, as we just have mentioned, from the phonetic dictionary. So if at an instant t the chain is in state Si, then Pij gives you precisely the probability that at next instant the chain will be in state Sj. So, so this is not just a Markov model, Markov chain, but it is hidden Markov model, which means that we have no direct access to the states of such a Markov chain, because I have direct access only to what I hear. I don't have the access of what you intend to say. So for that reason, it is called a hidden Markov model. Okay, so instead of what we do have access is a set of observables, which are the possible manifestations of the states S1 up to Sk. And notice that, in fact, the number of observables need not be equal to the number of states, because here we have n many observables, but k many states. And in general, n will be larger or equal to k. So we are also given so in our example with speech recognition, these observables will be the feature vectors that are extracted from each waveform of the phoneme. So O1 will be a vector of certain features, O2 similarly, and so on. So we are also given a matrix of size k times n, so that entry ik represent the probability that when chain is state Si, the observable outcome will be OK, right? So in the example with the speech recognition, so here, for example, we have phi 2, but this phi 2, we cannot directly observe it, can cause observation O, say, n1 up to O, n, m, but not equally likely. There will be, in general, the highest likely one, what you observe when someone pronounces the phoneme phi 2 and so forth. But they are all probabilities, right? This is the probability that's actually E in what I wrote, so let me be consistent. So this is what's called emission probability, so that, and let me write it like this, so that state phi I causes observation OJ, right? And these are probabilities. They, of course, have to sum up. So sum of emission probabilities of phi I causes J, for example, when J equals from 1 to n, that should equal to 1, right? Because every phoneme has to cause some observable, but this is the probability that the phi I causes observable OJ is given by this matrix, right? That is of size k times n, where k is the number of states. Sorry, I is the number of states, and k is sorry, I'm looking here. So this is the number of states times the number of observables. So we are only sure about which observables we have seen. So here you will have also observables, and all that we can tell is which observables we received or perceived. And now we would like to know, but what we want to know is the true sequence of the phonemes. So how do we find, of course, this is a non-trivial task. So instead of solving that, we simply look for what is the most likely sequence of states which would produce the sequence of observables that you saw. So that's a very interesting question. So Yusuf says, so O is also a Markov chain. That's a very good question, whether you can treat it as Markov chain, because you don't have probabilities here between the observations. You only it kind of goes roundabout through the observables. So probably it would not qualify that this is also a Markov chain, because it would be conditioned on the observable. Let me think about that. That's a brilliant question. You are really smart cookies. Okay, so now so that's exactly what we said so far. So now we chose the sequence of states that has highest likelihood. What is likelihood? Well, in a sense, likelihood is an inverse of probability. In what way? You see, assume that you have a possibly biased coin, so that the probability of a tail is P. So probability of a head is then 1 minus P. And then if you know P, you can compute explicitly the probability to get this outcome, right? How do we compute that? Well, probability to get a tail is P, and because these are two independent tosses, so it will be product of, again, probability to get T, so this is P times P. Then probability to get a head is 1 minus P. And then again, we have two tails, and in the end, we have a head. So, and this gives us p to the fourth times 1 minus p squared. So if you know the probability of whatever of the outcomes that generate our sequence, you can easily compute the probability to get that sequence. Now, likelihood, on the other hand, is when you invert the question. So assume that you have a coin with an unknown probability p of getting a tail, and you would like to find out about that. So assume that you toss it 6 times and you got the outcome that we just had up here, tail, tail, head, tail, tail, head. Now what you can ask yourself, which was the coin? So you still don't know. If you just know a bunch of a finite kind of sequence of events of tossing a coin, you cannot unambiguously determine what's the probability of getting a head in your of your coin, right? It would take an infinitely long chain to kind of asymptotically compute that probability. But if I just give you, if you have just one outcome, you cannot tell what's the probability of a head. But what you can ask yourself is, what is the probability of getting a tail that is the most likely to produce such outcome, right? So you want to, so you do your experiment, you toss your coin, you get tail, tail, head, tail, tail, head. And I ask you, okay, so what is the probability of the tail of your coin? Well, of course, you cannot tell me exactly, but you can tell me for what p, what probability p makes this outcome the most likely. So a lot of algorithms in machine learning rely on essentially making the guesses that would correspond to what's called maximum likelihood guess. So let's see how would we compute for what p the likelihood is the largest. Well, we will say, let us assume that the probability of getting a tail is equal to a variable p. And now we want to see for which p the likelihood of this sequence is the largest. Well, for this sequence, we just saw if the coin has probability of tail p, then p to the fourth times 1 minus p squared is the probability that you will end up with this sequence. So now what you can do is you want to see for what p is this expression which represents probability to see what you have already observed, right, is the largest. So to get for which p this is the largest, we just find partial the derivative with respect to p, set it to 0, and see whether we get a maximum or minimum. So if you differentiate this function with respect to p, this is what you get. Just it's a differentiating product of 2 powers. So it's the derivative of p to the fourth, which is 4p cubed, times the second factor is 1 minus p squared. And then you have plus, which will become minus eventually, 2 which is, so it will be p to the fourth. So this here is p to the fourth times, when I differentiate this bracket here, I get 2 times 1 minus p to the first power, right? and then I have to multiply by minus because I have minus p, so times -1. And that's precisely what we have here. And now you can, so notice this sequence will be totally unlikely if p was either 0 or 1. If it was 0, you can never get, I mean, it would be extraordinary if you got 2 consecutive t's. And if it's 1, it would be unlikely that you would get any h's, right? Any heads. So we can rule out that p is 0 and p is equal to 1. And so consequently, we can divide both sides by p to the third and divide by 1 minus p. And lo and behold, this gives us what's left here is just 4 times 1 minus p, and what's left here is just minus 2p, and then this is just a single equation. Okay, so that's, so the question is this. So the answer is the frequency of getting a tail, which we can just count, right? Well, you want a strict mathematical proof that a likelihood is in fact the frequency of the tail. And sometimes likelihood of, in this case, it's relatively easy to see it and you get the expected answers, but sometimes that's not the case if your random variables are much more complicated. So if you solve this, you get p equals 2/3, which makes 1 minus p 1/3. And so probability to get a head is only half of the probability to have a tail. And this is kind of consistent with what we observed, because we did observe 4 tails and just 2 heads. So the number of heads is in fact about 1/2 of the number of tails. So you would then guess, as maximum likelihood criterion will tell you, that the probability, the most likely probability that caused this sequence is p equals to 2/3. Now, okay, so in general, if you have an observed outcome, for example, there might be handwritten digits that you want to recognize. So when you have an observed outcome, something that looks like, it looks like this, say, what digit does this correspond to? Well, you cannot quite tell whether I was sloppy and whether this corresponds to 1/6, or sorry, whether this corresponds to 6, or it corresponds to 0, right? And I would say probably it's more towards 0, so we can give a probability, I don't know, say 2/3 and 1/3. So if you have, so when you have an outcome, right, a sequence of observables, then what you can ask that you know come from certain probability distribution, asking what is the most likely probability distribution to produce such an outcome, and accepting this as your guess about this the parameters of this distribution, that's called maximum likelihood estimation. Okay, yeah. Very good. So the likelihood, yes, so the likelihood is probability of P given the outcome TTH. Yes, that's correct. So, and you see, maximum likelihood often produces very good estimates of the unknown parameters, as we will see also later in the course. But sometimes, if the sample is small, it can produce very bad estimates. In fact, if the number of samples seen, if it grows arbitrarily large, then one can prove that, in fact, maximum likelihood will converge to the right estimate. But for small experiments, it can mess up things tremendously. Here is an example. Assume that I have given you a box which contains n balls, which are numbered consecutively from 1 to n, but I do not tell you what n is. So what you are allowed to do is to draw one single ball out of the back of the box and look at its number. And then you have to estimate how many balls there are inside. So so assume you did draw a ball and it turns out that it's numbered K. Now, if there are n balls in the box, what is the probability to draw any particular ball if they are all equally likely? If you have n balls. 1 over n, correct. Now, for what n will probability to draw ball K be the largest? What do you think? Well, if probability is 1 over n, as n increases, the likelihood will decrease. So what is the maximum, when drawing a ball with number K on it, when would it be the most likely? How many balls inside? When K is equal to n, exactly, right? Because you clearly know that there are at least K balls inside because you drew ball K. But getting we know that n is bigger or equal to K. The probability to draw any ball is 1 over n, right? Which is smaller or equal than 1 over K, because n is bigger or equal than K. So this means that the highest likelihood will happen when n is equal to K. So maximum likelihood will tell you you should guess that the number of balls in the box is just K. Well, let's see how good is such an estimate. So how good is this estimate? So probability 1 over n is probability to draw any ball from the box. And so probability to draw box, so what is then the expected value of your estimator? Well, the expected value is I times the probability of drawing ball I, which is times 1 over n, right? So if you sum this, 1 over n goes out and you have sum of I, and this is of course n times n plus 1 over 2, because that's just a simple arithmetic progression from 1 to n. So the ratio is then n plus 1 over 2. So the expected value of your estimator is essentially only 1/2 of the true value, right? So this estimator is extremely biased. An estimator is biased, right, if the expected value of the estimator doesn't match the true value. So maximum likelihood estimator did a very poor job. What do you think? Can you think of a better estimator that would actually be unbiased? Just imagine you took a ball out of the box and you see K. So what would you argue, what is the number of balls inside? If you have numbers 1 to up to K, I'm sorry, up to N, and you randomly pick one of them, what will be the expected value of what do you expect that you will see? Right? You are most likely kind of heuristically, right, to pick something that is in the middle between 1 and n if you do lots of drawing, right? So it would be n over 2. So an estimator that says double this and subtract double whatever outcome of your experiment is and subtract 1, then the expected value of y will be equal sum of I goes from 1 to n. The value of the estimator is 2i minus 1 divided by n. So you can decompose this in this way, and then you get one arithmetic progression here, minus you have just ones, 1 over n. So this is just n times 1 divided by n, you get 1. And this is just 2, and the arithmetic progression, when you sum it up, is n plus 1 divided by 2. So this is just, in fact, this minus 1 will cancel after I cancel n and 2 and 2, I get n plus 1 minus 1, which is just n. So this estimator that doubles the number that you drew and subtracts 1 would be much better than maximum likelihood estimator. But you see, this is due to the fact that you draw just one sample. Maximum likelihood actually has excellent performance if the number of samples is large, and in the limit it tends, so it's unbiased, in the limit tends to the true value. Okay, so now we come back to, hopefully we now understand what the likelihood is. So that's simply deciding which values of the parameters make the probability of observing your outcome as large as possible. So you saw the sequence of observables y1, y2 up to yt. And you want to find what is the sequence, true sequence of states x1 up to xt of the Markov chain, such that the outcome, the likelihood of the outcome is as large as possible. Okay. So in a sense, we are looking for the most likely cause of the sequence of the observations with the hope that it will be most likely that we are right. That's the heuristic behind it. So in our speech recognition example, we are given sequence of feature vectors F1, F2 up to F10, and we had 10 phonemes on that were pronounced. And now we want to see what is the sequence of 10 phonemes that that is the most likely cause of observing these outcomes. So theoretically, we could solve this problem by brute force. How would you do it? You could go through all possible sequences of states, of T many states, right? Of as many states as you have observables. And you can compute the corresponding probabilities that each of such sequences might be the cause of a given sequence of observations, and then simply select the largest. So if you have, so the two events have to happen, right? The first event is that the particular sequence of the Markov chain took place. So that's one thing that can happen. And the second thing is that the states caused exactly the right observables, right? So this is the probability of the sequence of states to take place in this order. And then we have another component, which is, we have to multiply this. So let me go back to what I draw. So now you have to multiply this with probability that X1 caused Y1, so that the state X1 caused emission Y1, stage 2 caused emission Y2, and so forth. So if you multiply this together, right, the total probability will be, so this, what I just explained, computes the probability that sequence of states, particular sequence of states, produces observable outcomes Y, and this is simply a product of the probabilities that X1 causes Y1 all the way to XT causes YT. And then the total probability of the whole event that that particular sequence X took place and that it produced the right observation is just the product of these two probabilities. And clearly this is easy to do when I give you any sequence of states. It's easy to compute its probability that this sequence takes place times the probability that it produced the right outcomes. And then you take the largest of these. Okay, so now this looks as a trivial problem. It's just a lot of computation, but notice the search space is truly gigantic. If the total number of states is k and the observed sequences of length t, then you have k to the power t many sequences to try, right? Which is just gigantic number. It's 2 to the power t times log k, right? So this is a gigantic number. It's exponential. So you cannot possibly do that. If you are building a speech recognition software, it has to be reasonably efficient. And in fact, what the Viterbi algorithm does, it simply computes using dynamic programming what is the most likely sequence that could have caused the observables that we saw. So before we turn to, well, maybe we can better finish this. I need a short break. So how does Viterbi algorithm work? So we have to solve. So let me write this like this. So this is state S1, S2, S3, up to Sk. And for each of these, we have probability P1 by 2, that this will be the starting state, by 3, and so forth. Here is the probability pi 4. So pi I is the probability that word starts with, sorry about that. So this is the probability that the word starts with Si. Then what you have, next state can also be S1 or S2 or S3 or all the way down to Sk. And we know probabilities of switching from each state to any other state that will be the state, this goes somewhere here, that will be the state in the second element, in the second step. So this is t is equal, sometimes we take it at 0, sometimes we take it as 1, so let's start from 0. This is t equals 1, and so forth. Now, the idea is you want to find essentially a path through this matrix that is the most likely to produce the given observations. So all of these states with given probabilities can produce outcomes, say OM. OM1, here's the outcomes OM2, and so forth. So what we do know is we know this sequence. What was the outcome here? What was the outcome here? And so forth. And we want to see which path through this, through this graph is the most likely one to be consistent with these outcomes that you have seen. So we want to solve, and the trick here of dynamic programming is that, lo and behold, you will find the most likely outcome such that, after I many steps, such that it ends with the symbol SM at the whatever will be ith step, right? So that you remember from 3121, we are not just asking across all states what is the most likely state to come to. We are asking what is the likelihood of the sequence of length I such that the very last state is precisely sequence M. Why do we do that? Just like in any other example with dynamic programming, it is because it makes the computation, the recursion, very simple. So Lik is the largest possible probability for which there exists a sequence of x's up to xi, so that the endpoint is Sk, that causes the sequence of observable outcomes y1 up to ya. Well, the starting point is, of course, you look at the first symbol, and you have y1 as observable. Well, probability to have sk symbol and observe y1 is equal to the probability pk, that the starting symbol is sk, times the probability that this symbol sk caused observation y1. So that's the bottom of the recursion, and then the recursion simply says the following. Let me draw. So here is instant, this would be instant I, and here is instant I minus 1. And we assume that in the table we have already computed likelihood of, sorry, let me make it, that we have already computed the likelihood that at the stage I minus 1, we ended up in state S1, which is the highest likelihood that in states that in previous step of time, right? You have here the largest likelihood that the state will be S2 and so forth. Now, for every state here, let's say state Sk. What does dynamic programming tell us to do? Well, simply look. So for this state Sk, you can find easily the emission probability so that kth state produces the outcome Yi, right? You can find it from the table. And then you know the probabilities of flipping from S1 to Sk. So then the optimal way to get to the Sk will be the minimum of optimal way to get to S1 times probability that from Sm we flipped to state Sk, and then this part is fixed, right? For doesn't depend on M, because this is just depends only on the arriving state Sk and the corresponding observable. So to get this the highest likelihood, you simply find the prior state, the time equals I minus 1, to end up in a state M times the probability from Sm to flip to Sk. In fact, I could have, which might have been better, put the bracket here for this max and then just multiply with this constant Sk times Yi. So a very good way to understand this is just if you remember this dynamic programming problem from 3121, when you have two factory conveyors, right? And you have workstations that can do the certain stages of assembly. And then what we were looking for was the path. And of course, you have how much time you consume to move across the two conveyor belts, right? And if we are looking for the path that, in this case, that minimizes the total time taken. Here, instead, we are looking for a path. We won't have only two, but as many layers, right, as we have the states. And we simply see for this one, you see, if L I minus 1 S1 times S times the probability to go from S1 into Sk is larger than Li minus 1 S2 times probability to go from S2 into Sk, and so forth for all other states, you look for the largest product, and this is your value of Lik. And of course, you can always put pointers back. If, for example, S2 wins, then you will set a pointer from Sk to S2 so that you can backtrack to recover the sequence that produced the largest outcome. So it's pretty straight forward, very logical algorithm, but it's extremely important because it replaces an algorithm that by brute force run in this time. It replaces it with the algorithm that ran, let's see, in what time. Well, this recursion has to be done for every initial segment out of T. Now, at any point, right, you have to fill the next layer of states, and there are k many of them. And then for each state, you have to look which combination out of k possible many is the best. And so you have to multiply everything by k. So this is T times k squared. So instead of this, we got something much, much faster. Okay, so I'll give you an example now that will hopefully make this clearer. So let us just make a short break. I have to recuperate my throat, and then we will continue. Okay, let's continue. Hopefully I can last another hour. So here is your problem. So in California, there are twice as many raccoons as possums. So this is important piece of information, twice as many raccoons as possums. So you got a job with Google and you are in California and you are observing your backyard, but it is dusk, right? So the probability that you think you saw a raccoon when in fact you are actually looking at a possum at a distance is 1/3. So you, with probability 1/3, you think you saw that you saw a raccoon, but actually you are looking at a possum is 1/3. The probability that you think you saw a possum while you are actually looking at a raccoon, so possum while you are looking at a raccoon at a distance is 1/4. So raccoons move in packs. So if a raccoon comes to your backyard, the probability that the next animal to follow will also be a raccoon is 4/5. Possums are solitary animals, so if a possum comes to your backyard, this doesn't impact the probabilities what the next animal to come will be, a possum or a raccoon. But you should remember that in California, there are twice as many raccoons as possums. Now, you believe that that evening you saw 4 animals. First you saw a raccoon, then you saw possum after another possum, and finally you saw a raccoon. Given such a sequence of observations, you see, it is not most likely what you should conclude is not that you definitely saw a raccoon, possum, possum, a raccoon, but you want to pick the sequence for which these observations are the most likely. Okay, so let's now extricate from this text all the information that we need to set up the problem. So what are the probabilities of initial states? So you see, it says in California there are twice as many raccoons as possums. So what is the probability that the first animal that comes will be a raccoon, and what is the probability that the first animal that comes is a possum? What would you think? If there are twice as many raccoons as possums, then with probability that you saw that the first animal to come, not what you see, but the first animal to come is a raccoon, will be twice the probability that it is a possum. So starting probabilities will be it's a raccoon with probability 2/3, and it's a possum with probability 1/3. Okay. So now we have to see what the probabilities of transitions are. So here it is, probability of raccoon is 2/3, probability of a possum is 1/3. Now, transition probabilities. Probabilities for after a raccoon that comes another raccoon is 4/5. Where do we have this from? It's this, right? Probability that if a raccoon comes, probability that the next animal to follow will also be a raccoon is 4/5. But this means that probability that after a raccoon, a possum comes is 1/5 because they have to sum up to 1, right? It's either raccoon or possum. So similarly, probability after a possum to see another possum, because possums are solitary, the probability is exactly the probability simply that a possum comes, right? Because the fact that previous animal was also a possum has no effect on the second time will be also a possum, so this remains 1/3, right, that we had here. So now, what are the transition probabilities? The last one that we have to take into account, well, this is probability that after a possum, a raccoon comes will be 2/3, again, because if a possum comes, then whatever next animal comes is an independent event. So it will be just 2/3 from here. Now, then emission probabilities. If you are a probability to think that you saw a raccoon when you were actually looking at possum is 1/3, and this was told we were told this is here. right? Probability that you thought that you saw a raccoon when you are looking at the possum is 1/3. Similar, but then probability that that you think that what you see is possum, looking at the possum, must be 2/3. Again, because they sum up to 1. Then probability that you think you saw a possum while you are looking at a raccoon is 1/4, which is here, right? Probability that you think that you saw a possum while you are looking at a raccoon at the distance is 1/4. And finally, we have emission probability that you think that you saw a raccoon when you are looking indeed at a raccoon is 4/5, because the probability that you thought it was a possum is just 1/4. So here then, as a homework, execute the Viterbi algorithm by hand. You can use a calculator to see what actual sequence of animals is most likely to cause the sequence of these observations, right? So how would Viterbi go? Well, initial probabilities we just had, right? Initial probability for a raccoon is, what did we have? 2/3. And initial probability for a possum is 1/3. Then at the next step, states are also a raccoon and possum. Now for a raccoon, after that a possum arrives is, here it is, let's see where it is, after a raccoon that possum arrives is 1/5. So here is 1/5. And then probability, that after a raccoon, another raccoon comes is 4/5. And similarly, you have here, after a possum to arrive a raccoon, the probability is 2/3. And then this probability must be 1/3. So here the probabilities are, if you are seeing a raccoon, there are two emission probabilities. One is that you think that you saw a possum, and this probability is, so let's see, where is the, so that you see, that you think that you saw possum when you are actually looking is 1/4. So here you get 1/4. And then, of course, oops, did I make a mistake here? Is this, it's not 4/5. Possum is one, no, this is 3/4. I don't know what possessed me. So this is 3/4. So here is 3/4 for possum, and this is that the emission is raccoon. So I should use small letters here. So the emissions are with small letters. So this is small p, and this is a small r. And so the likelihood that at first step, you see that the first animal is raccoon is equal to pi of a raccoon, right, times emission to think, what did we say? We thought that first is raccoon, that the first animal is raccoon, and L1 possum is probability that it is possum times, oops, so here is, I forgot the, times raccoon, and here will be O of so this is the probability that the possum has arrived, and you think in fact that it is possum. Is that right? Yeah. No, that it is a raccoon. It's raccoon given that it is a possum. So these are the starting values for L. Now, how do you choose L, the likelihoods here? When you have two choices, either you arrive here from here, or you arrive from here, here, right? And you take max of the two, and you continue in this way. So do it by hand. It's a really very good exercise to kind of get your an clear idea how the Viterbi algorithms work. Yes, 3/4. Thank you very much. I messed it up here. I'll correct the slides that are on the web. Okay, dokie. So that's all about the Viterbi algorithm. And next thing that we want to do is the universal hashing. Now, let me see, it's 5:30. Okay, I guess we have enough time to start working on this. So here is a scenario. We will finish it next time, but let's start. You are given an assignment to implement hashing, and you work in pairs. You test your opponent's, your pair, you take his implementation of a hash function and you test it and grade it how good job it does. Now, but your partner plays dirty. What he does, he analyzes your hash function and then tests your hash function with the worst possible sets of keys. Namely, he chooses the keys so that they would elicit a huge number of collisions, most of the keys going into the same slots. And you expect this from him. What would you do to defeat his malice? How would you, what does your algorithm have to do so that once it starts running, whatever your partner, even if he knows the content, the code of your function, he cannot propose a sequence of keys that will elicit worst case behavior. How would you do that? What should the algorithm do? Well, how do we design an algorithm that even if your partner can see the code, he cannot cook up a sequence that or set of sequences that elicit the worst case performance your hash function choice should be exactly randomized. So this is Michael. Exactly. So what you want to do is you want to randomize your hash function. So before the hash, on the first run of the hash function, the program will actually make a random guess and then design a hash function that depends on this random guess. So how do we do that? We want to pick a hash function randomly in a way that is independent on the keys that are actually going to be stored. So in this case, no single input always evokes worst case performance. So it will guarantee, you have to be very careful. So it will guarantee good performance on average. If you have, so you have your application and it involves hashing. You pick this random element and then you freeze it, and for as long as your program executes, you keep the same hashing, but on the next run of your program that utilizes hashing, your program will automatically choose a random object different from the previous run. If you do this many times, as we will see, you will be guaranteed that on average, your hashing will be extremely efficient. So let's see how we do that. So the trick, and it is used in different variants in many constructions. And here we will now see the simplest one. So we define that a finite collection of hash functions that map a given universe U into oh God, I hate this. Given universe U into much smaller range from 0 to n-1. We say that family H is universal if the following holds. For each pair of distinct keys from the universe, so you do the following. So here is the collection of your hash functions. So this is H1, H2, H3, up to whatever many you have, HK, say. So this family will be universal if whenever I take arbitrary two keys, X, distinct keys, X and Y, and I freeze them now, and then I go through the whole, oops, sorry, so this is the, not U, universe U, this is the H universe, right? So these guys belong from universe U, but these guys belong to universe H. And then you look which functions collide your X and Y. Say this is this subset H bar of H. We say that the family H of hash functions is universal if for any two keys X and Y, the total number of hash functions which will collide X and Y is equal to, so cardinality of this is equal cardinality of H divided by M, when M is the size of the table, right? So whenever you have arbitrary two keys, if you go through all possible hash function, x and y will be collided exactly in cardinality of h divided by m many instances of a hash function. So the total number of hash functions that collide x and y will be equal to the total number of hash functions divided by n. So now, so in other words, if you take any two keys, x and y, and you randomly pick a hash function from h, the chase of collision will be the same for all x and y, and it will be precisely 1 over n, right? Because cardinality of h, the probability is cardinality of h bar over cardinality of h, which is equal cardinality of h divided by m, divided by cardinality of h, which is of course just 1 over n. So assume now that you have a family of hash functions such that is universal. So let x and y be two arbitrary keys. For a randomly chosen h, we let the random variable cxy be just the indicator random variable. So it's equal to, it has only two possible values. It's either 1 if the keys x and y collide under h, or it is 0 if they don't collide. So this indicator variable is, so here it's not x and y that are chosen randomly. They are chosen, they are just arbitrary two keys, but they are frozen. It's just x and y. And random event is which h you choose. So x and y are fixed, but you arrange with the hash function over the whole universe, and c of xy will be 1 if x and y are collided by this h, and 0 otherwise. So let us now fix just x. Then by definition of a universal family, what is the expected value of E of C xy? Well, the expected value of this variable is equal to the probability that the two keys collided times 1, because in this case cxy is 1, plus probability that they didn't collide times 0, because the value in that case is 0. And here it is. So here this is on top probability, the number of hash functions that do collide over total number of functions. So it's precisely this probability times 1, and lo and behold, this is 0. This is 1, so the expected value is 1 over m. Now, assume that you have a universal family H, and assume that you are hashing n keys into a hash table of size m. And let's denote by Cx the random variable that is equal to the total number of collisions which involved key x. So this means Cx is sum over all elements that are not equal to x times indicator variable 1 or 0, depending whether y and x collided. Now, then the expected value satisfies the expected value of Cx. We can go with expectation, so this expectation can go inside of a sum because expectation is linear, right? But we know that we just saw that the expected value of this variable is 1 over m, and we are summing over n minus 1 instances because total number of keys is n. So those that are not equal to x, there are exactly n minus 1 many of them. And probability of, and the expected value of Cxy is 1 over n, so you get precisely n minus 1 over n. Now notice, one important thing is we are not claiming that these guys are independent. It might be the case that your hashing, even though it's universal, has a inconvenient feature that whenever, say, y and x collide, also y and z collide. But these events, but the expectations, this formula holds true regardless of whether these variables are independent or not, right? Simply because expectation is a linear operator. But what does this mean? It means that for every x, the expected number of collisions, if n is smaller or equal than m, so if you are hashing at most m elements into a table of size m, the expected number of collisions will be then smaller than m minus 1 divided by m, so it will be strictly smaller than 1. So on average, you will have less than 1 collision per slot, right? When you hash n elements into m slots. So essentially, on average, all of the slots will be very sparsely populated because the probability, the expected number of collisions is for every x is smaller than 1. Okay, so what can we conclude from there? So by the way, so this is why the excuse me. So this is why the universal hash family of universal hash function is so good, because when you use them, the expected number of collisions in each slot is less than 1, right? So in all likelihood, there will be very few collisions in each slot. Okay, that's very nice, but how do we design a universal family of hash functions? Well, first we chose the size of hash table to be a prime number, n. So now you do the following trick that is kind of quite often used. Given the size of your universe of all possible keys, you take R to be the log of the size of your universe. If you take such an R, then this universe will be in size between m to the r and smaller than m to the r plus 1. Log was taken here with the basis m. So now what we do, we represent each key x in the base m. So what does it mean? It means that the digits of the representation, let's call them xi, so the digits, all xi will be smaller than m and bigger or equal than 0, because they are the digits in the base m. And then we have m to the I. So why do we do that? The idea is to avoid very large numbers, right? You see, X can be gigantic, but then we replace X with a vector X0, X1, up to XR, such that every Xi is smaller than M. So you will have, so all the coordinates of X will be small because M is just the size of the hash table. So it's much smaller than the cardinality of the universe. Then what you do, now this is, and you will see it over and over again, and if you study any kind of modern sophisticated randomized algorithm, there is a very large probability that you will see precisely this trick. It's a trick of a random projection. Essentially what we do is we choose a vector of integers that are between 0 and then -1 completely randomly. And then what we do, we define the corresponding hash function for this vector A as the scalar product, essentially, of the vector X and vector A mod M. Because how do we compute this sum? This is Xi times AI, sum from 0 to R. This is precisely the dot product, also often this denoted just like this, mod M. Right? So the scalar product, even though the length of A is not unit, you see, if A is corresponded, if the norm of A, the modulus of A, vector A, was 1, then this would be just the value of the projection of X to the vector A, but here we have to multiply, so this, we have to multiply it with the length of vector A, but this is a constant, right? So this value really kind of corresponds. So this is your A, this is X projected to A. Yeah? So essentially, the important part here is the size of this projection, and then it's modded out by M. Okay. So now we want to show that with these hash functions, the family of thus generated hash functions is universal. So how do we generate any hash function from this family? We generate it simply by choosing randomly R+1 many numbers that are smaller than n. So that's, and then we do hashing using this formula. Now, I claim that with a hash function chosen in this way, right, that the family of such hash functions, when A ranges through all of this will be, there are m possible entries from 0 to m minus 1. So it's m to the, so what did I want to tell you here? Sorry, I'm not feeling very well today. Define the corresponding function. So right, so there are m to the power R+1, right? So for each such vector, and there are heaps of them, m to the power R+1, you have a hash function like this. And now our aim is to show that in this way you get a universal family of hash functions. right? So these are hash functions in which A ranges through all vectors of this form, right? M entries, sorry, R plus 1 entries with from 0 to n minus 1. And we want to show that, in fact, such family is universal. How do we do that? So assume that X and Y are two distinct keys. And let's examine when will these two keys collide with such a family. So let X0 up to XR and Y0 up to YR be their corresponding. So what is here? X is sum when I goes from 0 to R of xi times m to the I, right? This is how we get this vector, simply by representing x in the basis, in base n. And you do the same for y's. Then, when will x and y collide? Well, this means that this equality has to hold mod m, right? Because this mod m equals to this mod m is equivalent to this equals to that mod m. And now I can move this onto the same side of the equation, and I get that the collision happens precisely when I equals from 0 to r of this linear combination is equal to 0. Okay, now x and y are two different keys. And so consequently, their representations in basis n must be distinct. So at least one coordinate, ith coordinate here, is distinct to I coordinate here. So without loss of generality, we can assume that that's the first coordinate because the argument is equal, it's completely the same for any other coordinate. So what do we then have? You see, if we will keep on this side only x0 minus y0 times a0, and then sum that goes from 1 to r, so the remaining part of the sum, we move to the other side of equality. Now comes the trick. If this is true, and if this is not 0, because the size of our table, namely m, is a prime, then mod m, every non-zero element has an inverse, right? So if m is a prime, for every non-zero element, so I shouldn't have put the 0 inside here. So for every non-zero element z between 1 to m minus 1, it has a multiplicative inverse, namely z to the minus 1, which is any of these numbers, whatever it is. When you multiply by z, you should get 1 mod m. Okay. So because we assumed that x0 is not equal to y0, I can divide both sides by this quantity, x0 minus y0. So here I'll have this multiplied by the inverse of this and then mod n. What does this tell us? That if it means that if any two keys such that x0 is not equal to y0, and for any randomly chosen r plus 1 numbers, this should have started from, actually not, this is not, sorry about that, I will correct. this. So this is not R plus 1, but just R numbers from 1 to R. There is exactly one element A0, so that the corresponding function that is obtained when you concatenate A0 to the front of A1 up to AR, there is a unique A0 so that X and Y collided, right? So now it's just a simple arithmetic. So if I choose this randomly, A1 up to AR, there is a unique way to extend it so that X and Y collide. But how many ways can I choose these guys? Well, clearly, there is M to the R sequences, right? Because each of them can be from 0 to M minus 1. So there are M options, and the length is R. So this will be M times M times M R times, so M to the R sequences. And each such sequence allows unique extension that collides X and Y. But in total, we have M to the R plus 1 sequences of length R plus 1. So we have probability to randomly choose a sequence from A0 to AR such that X and Y collide is the total number of elements, total number of choices that you can have to collide X and Y divided by total number of choices of such vectors, which is M to the R divided by M to the R plus 1. And this gives you precisely 1 over M. So lo and behold, the family is universal. Okay, so let's stop here. We will continue on Wednesday. Please read carefully. Do the exercise with the Viterbi algorithm, and I will give you a solution so that you can check whether your calculations are right. And read, please, this about universal hashing, because it's extremely important, and the same ideas will be used over and over in the rest what we are going to do. Okie dokie, you are most welcome. I'll see you on Wednesday. Please study hard. Bye-bye.
Thank you, Al. Thank you, Alex.